Good morning, everybody. My name is Devashish. Uh, Thank you for inviting me. It was a very pleasant surprise. And today I hope to tell you something interesting about security proofs for decoy-state BB84. Okay? So, okay. So what we will focus on during this tutorial is things to do with protocol security for device-dependent utility. What this means is that we assume we have a mathematical model of what our devices are doing in the QPD protocol, and we wish to prove security within this mathematical model, right? And what I really want to focus on is stuff like common gaps in proofs, limitations in different proof techniques that we have available, comparisons between different proof techniques, and performance of proof techniques. In particular, what we will not really focus on is stuff to do with implementation security, DI, MDI, QKD, side channel attacks, hardware imperfections, and many, many, many other things that one could talk about in this area. Okay, so maybe a few simple slides to just warm us up. What is QKD? As a primitive, we have a two-party protocol. Alice and Bob want to create secret key at two distant locations. There's an adversary Eve that wants to know what the secret key is that is being produced. Alice and Bob have devices in their labs that they have characterized. They know what they do, and we have, as I said, a mathematical model of how those devices behave. There's a secure perimeter around Alice and Bob, so we know what information leaves their labs and what information comes in. And we have an authenticated classical channel for Alice and Bob to communicate. Everything that they say to each other is known to Eve, but Eve can't impersonate either one of them. Right? And we have an insecure quantum channel as well that Eve can attack any way she wants.
Can you speak up a bit?
Okay. And we also have true random number generators that Alice and Bob can use at various steps of the protocol. Okay. So we said we want to produce a key. What properties would one want from a key? So we might want a QKD protocol to end with Alice holding a key, Bob holding a key, Eve holding some information potentially on these keys. And we might hope that the final state that they get looks something like this, right? Where Alice and Bob have correct keys. They both agree on the key that is being produced. Each key is equally likely. So in this case, it's okay. I guess I've been asked to use this one, which lets me move around, which is good. So, okay, where was I? Yes, so each key is equally likely, and Eve completely factors off, right? There is no dependence on the key on Eve's register, on the state that Eve has. Okay, so in terms of protocol steps, what does QKD look like? We're going to have Alice prepare some states, transmit them to Bob, who's going to measure them. I think it might be the Iguana Tech plugin that's causing issues, but okay. So coming back, we have Alice sending a train of pulses to Bob. At this stage, Alice knows what she sent. Bob has measured what he measured, and both Alice and Bob are classical. Then we're going to have some public announcements where they announce some information in each round. Typically, it's stuff like what basis I used, did I get a detection, did I not get a detection, things like that. Then Alice is going to do some processing based on these public announcements. So she might choose to, for instance, discard certain rounds that Bob decided that Bob did not manage to get a detection on. And we have this raw key string of Alice, right, that she wants to use, that she wants to distill a secret key from. Then Alice and Bob are going to do something called as the acceptance test, where they check whether the public announcements that they've made belong to a certain predetermined acceptance set, which basically means they check if they're good enough. If they're good enough, they accept the protocol. If they're not good enough, they abort. Right? Okay, so some errors might have crept in. So Alice might send some information to Bob to correct these errors. And Bob is going to use this information to produce a guess for Alice's string, which we hope is correct. Then we're going to have error verification, where they're going to do a two-way protocol where they compare two universal hashes of their respective raw key strings. And if they match, they proceed. If they don't match, they abort. As a final step, we have privacy amplification, where one of the two parties picks a random to universal hash function, shares them with the other party. Both of them apply the same to universal hash to their raw keys and produce the final output keys. Okay, so this is roughly what a typical QKD protocol looks like, but there are many variations possible. So the obvious ones are, well, we have a lot of freedom in how we choose to, what states we choose to send, how we choose to encode them. Is Bob going to use active detection setups or passive detection setups, encoding degrees of freedom, etc. But we also have some more structural options available. Like we could decide to do on-the-fly announcements, where Alice and Bob might want to announce, make public announcements while they are sending quantum signals. This saves memory in actual implementations, but now you have to do your security proof in a way that allows Eve to potentially modify her attack based on these public announcements. One could also do variable length protocols, where instead of a binary accept decision, where you just either accept or reject, you have a more nuanced decision where you accept and also decide what output key length you wish to use. Okay, so I'm sure almost everybody here knows what BB84 is, but maybe a couple of slides on BB84. It is a part of my title. So in BB84, Alice has 4 possible states she could send in 2 bases, 0, 1, plus, and minus. Bob has 2 different bases he could measure in. Alice just sends a train of pulses. Bob chooses a random basis to measure in, and Bob gets certain outcomes. If they use compatible bases, then the outcomes are correlated. Then they have a public discussion over the authenticated classical channel. They figure out which rounds they ended up using compatible bases. On the rounds that they did not use compatible bases, they just throw them out. On the rounds that they did use compatible bases, they check whether they got an error or not. So they basically map whatever they had to raw key strings, and they check, right? And then we have this acceptance test, which is roughly going to look like checking a random position of these basis matched rounds and check if the error rate in those rounds is above or below a certain threshold. That is pre-decided. Okay, so where does this decoy state come from? So in real implementations, Alice is not going to send a perfect qubit. Those are hard to prepare. So she's going to send phase randomized weak coherent pulses, which have some photon number distribution. Right? And basically, threshold detectors can't tell the difference between whether they're measuring 1 photon or multiple photons. So Eve has the following attack, where she could steal 1 photon from all multi-photon pulses that get sent out. And she can wait for public announcement. She can wait until Alice announces her bases, etc. And she basically knows exactly what Alice intended to send. Right? What this means is multi-photon pulses leak all information to Eve. Okay? There's a solution. We're going to make Alice send phase randomized coherent pulses of different intensities, which are randomly chosen. Eve knows the photon number. She can check what comes out of Alice's lab, but Eve does not know the intensity. And because we're going to have observations from across different intensities, they allow us to gain some non-trivial information on Eve's attack on different photon numbers. Okay, that's the kind of general idea. Decoy states are typically not the problem in modern security proofs. And so we are not really going to talk about them too much beyond this point. I just wanted to mention them. Okay, so now we come to the security definition of QKD, where we are going to have some notion of an ideal protocol that runs and always outputs an ideal state that we would be happy to get. Then one has the real protocol, which is actually the one that you implement. And security is going to be defined as the scenario where the real output state is close to the ideal output state. That's the general idea, but a bit more formally, we have fixed line QKD protocol is secure if its output state satisfies this particular equation, where we basically have this probability of accept term sitting in front, and we look at the distance between the real state and the ideal state condition on acceptance. Okay. Note that for variable length QKD protocols, the security definition looks slightly different. Basically, we have, instead of just a single accept event, in which case we produce a key, we have many, many different events that end up producing keys of different length. So we have more such terms. And typically, you require different, slightly modified security proof for proving security for variable length protocols. They don't just straightforwardly follow from fixed length security proofs. But at the same time, all of the proof techniques that we use right now, basically, are able to prove variable length security in pretty much the same way they prove fixed length security, right? And they don't have any additional penalty. And so for this tutorial, we are only going to discuss fixed length security. Okay. All right. Okay. So note that the security definition does not say that the QKD protocol is epsilon secure if the real output state condition on accept is close to the ideal output state, right? You can kind of think for 2 minutes and consider the scenario where Eve intercepts everything that leaves Alice's lab and just forwards garbage to Bob. Now, no matter what happens in the protocol, she has access to everything that Alice sent out. So she can do error correction, measurements, etc. the same way Bob would have, and she knows everything there is to know. Okay? So basically, this probability of accept prefactor that is present in the security definition is actually quite important. All right, so now we can start doing some security proofs, and we're going to cover some steps that are common to across all the proof techniques that we talk about. So some fairly simple algebra and the triangle inequality lets us decompose security into two requirements. We have secrecy, where it basically looks like the security definition, but we trace out Bob. So we want Alice's key to be secret, close to ideal. And we have correctness, where we demand that the probability that the keys are not the same and the protocol ended up accepting is small. And the overall security parameter is simply the sum of these two security parameters. Typically, the correctness condition is fairly easy to satisfy using two universal hash checks during error verification. We will see that in the next slide. But the secrecy requirement is typically the one where we have to work a lot harder. Okay, so let's kind of do the correctness proof in one slide. So recall that we have Alice and Bob's raw keys S and SP, and they are going to do some privacy amplification on it to get the final output keys AA, KP, right? And we are going to do a step where we check whether the two universal hashes of these S strings match or not. Okay? This is going to look like this. So the first inequality simply follows because if you accepted the protocol, you know for sure that the error verification passed. So basic rules of probability. Same thing on the other guy. You know that if the output keys are different, then the raw keys themselves must have been different. We use, again, basic probability to rewrite these as conditional probability. We knock off the first term, so we're only left with the second term. And now we simply say that, okay, if the raw key strings were different, then the probabilities of error verification passing, which is the hashes actually agreeing, is small, right? Where we have 2 raised to minus LEV is the number of bits you hash. Okay, so we can set this LEV value to log 1 over epsilon correct to satisfy epsilon correctness. Notice that this argument has nothing to do with the rest of the QKD protocol, right? I don't need to know how I did my error correction. Even if I did it correctly, incorrectly, I really don't care. As long as I include this error verification step that compares to universal hashes of my raw key strings, I have correctness and I can move on. So I really like this. It's a fairly clean way to do correctness and then not bother with it for the rest of the proof. Again, notice that the claim is not that the probability that the keys are different condition on error verification passing is small. Again, you can basically go through this so-called garbage attack where Eve intercepts everything that Alice sends and forwards garbage to Bob to convince yourself that that claim cannot be true. Okay, so now we come to secrecy. And here we're going to use this thing called the leftover hashing lemma, where let's for now pretend that we know the state between Alice and Eve. And Alice samples a random to universal hash function that maps to L bits. She stores it in a register, applies it to her classical string S to get the final output.
I think that noise is coming from the 2 microphones. So
okay, that makes sense. Okay, so basically here what we have is this is the state that Alice gets. This is the state where the Alice's key is perfect. And we have that the distance between these two is upper bounded by the right hand side. And basically, I guess it's a little bit hard to see, but we can set this key length that we hash to be something like the smoothman entropy of the state minus some terms, and that lets us satisfy secrecy for some epsilon. Okay, this works very nicely if we know the Alice Eve state, but we don't know the state. Right? Eve is not nice. She does not tell us what attack she wants to do. And so the solution is to do some kind of worst case analysis over all possible attacks that Eve can perform. Okay? And so now for secrecy, our task is basically bounding the entropy that shows up in the leftover hashing lemma over all possible attacks. And obviously this is hard because this is a big protocol and we don't know what, we don't control Eve. Okay. Note that there are many different leftover hashing lemmas and there are a variety of entropies that can show up here. For this talk, I'm going to focus on the smoothman entropy because that's the most commonly used, but you could have others here as well. Okay, so we want to lower bound some entropies. What kind of bounds can we hope to get? Can we not hope to get? So you might ask for something like, over all possible attacks, the min entropy of whatever Alice holds, given whatever Eve holds, is greater than some non-zero constant. Right? And notice that we have to give all classical communication to Eve because we only have access to an authenticated classical channel. Nope, this is hopeless because the garbage attack, Eve can always intercept everything that Alice sends out, forward garbage to Bob, then this entropy is exactly 0. Or maybe slightly more than 2. Okay, one could try to condition on the protocol accepting. and then ask if the following bound can be shown to be true? The answer is no, because again, if Eve does this garbage attack, then Eve knows everything no matter what happens in the protocol. So you can condition on any event you like, but this constant is still going to be close to 0. Okay, so these two types of bounds are not going to work. What kind of bounds can work? We could have, we could condition on accept, but this time we could include the probability of acceptance inside the state, right? So this, when I write the thing with the vertical arrow, it means this is normalized. When I write the conditioning with the wedge, it means that it's not normalized, it's subnormalized. It includes the probability inside the state. Okay, these kind of bounds do work, and in the EUR approach, as we'll see a few slides later, one can show such bounds. The other possibility is we might demand that, okay, I want to condition on acceptance without dealing with this probability, but I'm willing to kind of have this log probability term be subtracted on the right-hand side. Okay? And these kind of things also work. They are used in the EAT approach typically, and you can kind of convince yourself, at least for the second line here, that if you do the garbage attack, then because the probability of acceptance is very small typically, the left-hand side could be 0, the constant could be high, but it could just be subtracted by the log probability. Okay, so basically both these options work precisely because the security definition includes this probability of accept term inside of it. Right? If you did not have this guy, then you would not be able to use these bounds. Okay, so I want to take a step back and look at sort of an overview of all possible security proof techniques. So we have what I would say leftover hashing lemma based proof techniques where we use the LHL to analyze privacy amplification. We need to estimate Eve's information on Alice's or Bob's raw key using some kind of testing information. And there are three main proof techniques we can use. One is entropic uncertainty relations, one is entropy accumulation, and post-selection technique. And these three are the ones that I'm going to talk about today. There is one very important and widely used proof technique called phase error correction, which does not go through the leftover hashing lemma. And it uses ideas from quantum error correction to effectively prove the same thing, that you can factor Eve out from the output key if you just do this two universal hashing procedure. I'm not going to talk about this specific proof technique, mainly because I don't know it as well as I do the rest of them. Right? So I would not be confident explaining phase error correction to you. And although it's very widely used in the field, but what I can offer is that this EUR proof technique and phase error correction methods are closely related. So in both of them, you end up setting up this thing called the phase error rate, and you end up bounding the phase error rate via some sort of sampling argument. And actually, there is a very nice equivalence between the two that was shown by Surumaru, which basically says that they're equivalent up to some trivial factors. Right? So we expect both of them to yield similar performance and similar key rates. And so I stick to EUR, which I know somewhat well. Okay, so again, we want to prove lower bounds of entropies that show up in the leftover hashing lemma. We have a variety of methods to do it, but before we see those methods, we actually might want to take a look at some miscellaneous tools that we use in order to prove these bounds. Right, so the first thing, very standard in QKD, is source replacement schemes. So what happens in a prepare and measure protocol is Alice prepares states, He sends them to Bob. Eve can attack the state Alice prepares any way she wants, and Alice's state preparation can be represented like this, where she stores her choice of signal state in the register X. Okay. Instead, one could imagine the following scenario where Alice prepares an entangled state on AA prime that looks like this, and then she simply measures the A system projectively. That basically cancels off all the off-diagonal terms and stores the outcome in X, and you end up getting the same state as the left-hand side. Okay, this is nice. So instead of thinking of the left-hand side scenario, we can think of it as the right-hand side scenario, where Alice is not preparing state, she's just doing measurements. What if Alice wants to send mixed states and not pure states? Basically, the same trick works. You have to include these things called shield systems, but I don't want to go into them right now. Okay, so we want to analyze scenarios that look like this, where we can notice that the A system never leaves Alice's lab, so Eve never gets to touch it, which means that the marginal on A that she has prepared is going to be the same. Right? Eve can't influence what row A looks like, no matter what she does to A prime. Right? So we in this scenario, we know that whatever Alice, Bob, Eve state we get, when we trace out Bob and Eve, we know what that thing is going to look like. Which means that prepare and measure protocols can be thought of as entanglement-based protocols, but with this kind of promise that Alice's part of the state is going to be fixed in law. Right? So this can be called the fixed marginal constraint or the fixed marginal promise, and it's actually quite important, and it ends up showing up in many proof techniques for prepare and measure QPD. Okay, we have source maps which work as follows. So we have a source that outputs some real states in the world that we want to analyze. They get given to Eve, but the real source can be thought of as a virtual source that produces some virtual states, which is then followed by a source map, right, that produces the real output state. Okay, if you can construct this virtual source and a source map that obeys this relationship, then you can invite Eve into Alice's lab for a bit and basically give Eve control over the source map. Okay, and if you do this, you are left with analyzing the virtual source, and the virtual source might be hopefully nicer to work with than the real source. Okay. There are many kinds of source maps that exist that are used. So one common one is the tagging map, where when you think of a phase randomized weak coherent pulse, we can recreate that by having a virtual source just cut off the higher photon number and output a classical flag, and then the source map just looks at the classical flag and prepares the photon number distribution on the higher than, let's say, 10 photons. And that allows us to not think of an infinite dimensional source, but instead think of a finite dimensional source, because higher photon numbers are cut off by a classical flag. Some imperfections can also be handled by, in some sense, putting them into the source map and then simply looking at the virtual source. Okay. We have squashing maps that basically do the same trick but on Bob's side. So Bob is typically measuring using infinite dimensional POVMs because he has threshold detectors. They are difficult to analyze on account of being infinite dimensional. One can try to show that this measurement can be thought of as a squashing map followed by a finite dimensional behavior. And if one can show this, then again we can invite Eve into Bob's lab, give her control over the squashing map, and then analyze just the finite dimensional squashed detectors. Right? Okay. There are again many variants of squashing maps, and the way they are used in proofs is also sometimes different. So we have the qubit squasher, for instance, which under some high symmetry conditions where all loss and dark counts, etc., in threshold detectors are equal, allows you to think of it like you're measuring a qubit. Right? We have the weight preserving flat squasher, which is a lot more general. It just requires some block diagonal structure and photon number that was invented a bit later. And both of these kind of squashing maps allow you to give Eve full control over the squashing. Okay? So in this sense, they are proof technique independent because you can first apply the squashing argument and at the level of the protocol itself, pretend that you're working in a protocol that has the squash detector, and then decide, okay, what proof technique do I wish to use to analyze this new protocol? Okay. Then we have this thing called the universal squasher, which allows you to do this trick, but only for the purposes of estimating phase error rates. So it's only used in phase error-based proof techniques. And obviously, it's limited to proof techniques that in which you want to estimate the phase error rate. So it's not a full equivalence of the measurement procedure, but more like an approximate equivalence. Okay. Then we have the flat state squasher, which is widely used. Here, the idea is you preserve all photon numbers coming in below a certain threshold, and whatever is higher than that threshold, you simply measure it and spit out a classical flag. Except that you need to enforce that there aren't too many classical flags generated by this squashing map, right? Because if it's a classical flag, then Eve knows it too, and you, in some sense, those rounds, Eve knows exactly what happened in Bob's lab. So you can't give the entirety of the squashing map to Eve. You have to somehow constrain Eve to not be able to put everything in the flags, roughly speaking. Then there is dimension reduction method, which is maybe not exactly a squashing map, but it allows you to convert a single round infinite dimensional STP, which shows up in some heat calculations, to a finite dimensional one. And the key point that I want to make here is that both of these, at least currently, cannot be applied directly at the protocol level, right? They can only currently be applied at the single round optimization level in most works, which means that they're dependent on proof techniques that allow you to first get to a single round optimization and then use these. Okay. Okay, I seem to be doing well on time, so I have some time to talk about this. So how do we handle information leakage due to error correction? Right? So we have this complicated entropy that we want to compute lower bounds on. The communication bits that we use for error correction and error verification, they are obtained by applying a giant matrix on the entire Rocky string, so they are a bit complicated to analyze. So we might want to use chain rules that look like this, and instead only have to worry about these nice round by round announcements that happen. And this chain rule exists, it's all well and good. And what the correction term that we need to compute is the number of possible transcripts that can exist in the error correction and error verification registers. Okay, so we have some options here. So one could think of the event as the acceptance event of the protocol. We could do an error correction protocol that sends exactly lambda EC bits. then the value of this log dimension term is the number of bits you used for error correction and the number of bits used for computing the error verification hash, which is log 1 over epsilon correct. Technically, Bob also responds with a bit that says, yes, my hash matched, yes, my hash did not match. But actually, that bit does not matter because if you look at the event where you accept, that bit is deterministically set to one value. So this is kind of fine, and this is what you want to do in proofs, except that you might want to say, okay, I want to look at the event where I accepted the protocol, I ran my error correction subroutine, and I look at the number of bits I actually ended up using, right? And that is, let's say, lambda EC ohms. In this case, you don't need to know what the EC protocol was because you know exactly how many bits you used. So this term is easy. And this chain rule also exists, so there's no problem. The problem is simply that now you want to analyze this guy condition on the event that your error correction protocol ended up using exactly these many bits. Okay? And it's just, we don't know how to bound this guy when we put this event in there, but we do know how to bound this guy when we put simply the accept event in there, right? And so what all of this tells us is that in existing security proof methods, you have to do your public announcements, and you need to fix what error correction protocol you're going to use and what this term is going to be in your security proofs at the level of at the stage where you do public announcements. Right? You can't first do error correction, look at how many you used, and then say, okay, this is how many I'm going to subtract. And this is an incorrect claim that I think even I made in one of my papers. Okay. So again, we want to prove lower bounds on entropies, and we have several tricks that allow us to consider scenarios where we have entanglement-based protocols with marginal constraints on Alice. We have finite dimensional sources. We have finite dimensional measurements on Bob's side. And we don't need to worry about error correction and error verification as public announcement. Okay, so now we start talking about some more interesting things, hopefully. The first technique I want to talk about is the post-selection technique. Okay, so the starting equation here looks something like this. But on the left-hand side, we have a permutation invariant state, right? Actually, let me go back. So we have a permutation invariant state. We have a constant that depends on different dimensions in your protocol, and we have an integral over some mixture of tensor products of IID. Okay? And because the left-hand side, this equation only holds for permutation invariant states, we need to argue that if the protocol satisfies this permutation invariance of the protocol, then we can, without loss of generality, only consider permutation invariant states in our analysis. Okay. If you do this, then in step 2, one can argue that, okay, because we have this operator inequality, we only need to worry about a purification of this state, right, which is a mixture of IID states. Okay? And in step 3, we want to say, okay, instead of considering a mixture of IID states, we only need to look at every possible IID state. Okay? And this is a generic kind of way to reduce security analysis of coherent attacks to security analysis of simply IID collective. The original post-selection paper contains an error in the last step, where you have to go from a purification of this guy to every IID state in the integral, which was patched recently, and the post-patch impact on key rate and the security parameters look something like this. So this G and X term that shows up here depends on the dimension of Alice and Bob. What this means is that in order to use this technique, we need to have finite dimensions on Alice and Bob before we apply the post-selection technique. So we need to use swashing maps and source maps first, reduce to a scenario where we have finite dimensions, and then we can apply the post-selection technique. Okay? Which means that the flat-state squasher, which is where we have to kind of constrain Eve in some sense and not give her full control over the swashing map, cannot be used directly with this technique. Right? And this is also another thing where it's often you'll see statements that, oh, by using, you have a paper that does IID analysis using flat-state squasher, and by the post-selection technique, it can be lifted to coherent attacks. It's not so easy. Right? Once you sit down to do it, it gets a little bit difficult. Okay. The other thing is that for prepare and measure protocols, we want this integral that shows up in here to only have states that also satisfy the fixed marginal constraint promise, right? Because we only want to analyze the IID states that show up here, and so if it's prepare and measure, we want these states to also satisfy the promise. And so we need to argue that appropriate definitive reductions also exist that preserve this promise in some sense. Okay, so this is what you get if you use the post-selection technique. Notice that there are two causes, right? Two separate changes you have to do. One is an impact to key length, which is typically fairly minor, and the other is the impact on the secrecy parameter, which is typically the one that is pretty large. And as I said before, the IID key rate calculation needs to be done over all IID states that show up in this integral. Okay, so let's say we want to use this technique. How can we prove secrecy for all IID states? This one is fairly straightforward. So this is the target statement we wish to prove for all IID states. We start with the set of IID states we care about, and we say, okay, this state is either bad, if it aborts with high probability, or rather, if it accepts with low probability, sorry. Okay? If it accepts with low probability, then just this term itself is small, and so the whole thing is going to be small, and we're going to be fine. Okay? If this state is not bad, then we have some knowledge about the state, and we can use this IID structure to say that, okay, the key length that we care about, we just need it to be n times the von Neumann entropy of a single round kind of state minus some constant. Okay? And then once we have this bound, we can use this in the leftover hashing lemma to obtain a bound that bounds the trace distance that we want. Okay, in order to do this, we do need to compute some numerics, which roughly look like this. So we want to minimize the single round kind of state on Alice given public announcements and Eve. We know that the state belongs to a set of density matrices. We know that it obeys the fixed marginal constraint, and because of some IID, the way we constructed the good set and the bad set, we have some more constraints on this state. Okay? And the good news is this problem is convex. It can be solved. It has been solved by a variety of methods. And there exists a nice, in my opinion, numerical package from our group that actually does this job. Right? And I think all of the papers from our group actually have code that can be found on this website. Okay, so All right, we can do the IID calculation as well. So why not use the post-selection technique? It sounds pretty great. It's not that great, mainly because we have to satisfy permutation invariance of the protocol in order to use this technique, right? And the way we can do it is we can actually implement a random permutation on the classical data we get right after doing our measurements, which is fine. But in order to say that that permutation lets us satisfy the permutation invariance, we need the measurements themselves to be IID. So we need Alice and Bob to do the same measurement using the same POVM in each round. And when we have any sort of correlated effects, like after pulsing, dead times of detectors, it's not clear how we would even get started. It's not clear whether the protocol would in fact be permutation invariant, and so how would you use the post-selection technique? The second problem is that it kind of fundamentally, this technique starts with this end round Alice, Bob, Eve state, in which Eve has already done her attack on all pulses that Alice sent out, right? And when we want to do things like on-the-fly announcements, we want to be able to, we want to let Eve modify her attack based on any public announcement that happens. And so it's not clear how this whole approach can be modified to let Eve modify her attack. Okay, and the third problem is that simply the penalty, this G and X value that you get is really very large, right? And so you get pretty low key rates if you use this technique. But it's fairly easy to use. It works for generic protocols. You don't have to kind of, I like to say that you can pretty much get key rates for most protocols within a week if you know how to set up the numerics. You know beforehand that the key rates are going to be bad, but you'll get them. Okay, so now I want to talk about entropic uncertainty relations. So here, the fundamental abstract statement that we want to use looks something like this. So we have Alice, Bob, Eve. We want Alice to measure her subsystems in the Z basis, and then we get some kind of classical string whose min entropy we wish to bound. And the EUR statement lets us obtain a lower bound that looks like this, where we have a state that shows up on the right-hand side, where we measure Alice in the X basis, right, in a different basis. Okay. Right now, this is Alice is classical, Bob is quantum. We can make Bob also be classical by asking Bob to complete or to measure his quantum system using any measurement of his choice. And then Alice and Bob both become classical. And then we want to obtain a high probability upper bound on the error rate between these two classical states, right? And that can be used to replace this max entropy term that shows up here. We have this n times CQ factor that shows up. CQ is basically the overlap between POVMs in the Z basis and in the X basis. For typical qubit BB84 type setups, it's typically the canonical X and Z measurement, so this overlap is typically 1. Okay. And so in this sense, we have this notion of a phase error rate, where we have a virtual an error rate corresponding to measurements that you don't actually perform in the protocol, and we need to obtain upper bound on this virtual error rate. Okay, notice that nowhere along this analysis does any notion of an IID state show up. Like in the whole approach using entropic uncertainty relations, we don't have to ever talk about a single round IID state. It works directly for the global state. Okay, so now when we apply this statement to QKD, what is the state on which we will apply the EUR? It looks something like this. Okay, so basically, we only want to keep the rounds that we want to use for key generation, right? Which means that we only want rounds where Alice and Bob have chosen to measure on the same basis. Bob is guaranteed to get a detection event, and we know that these rounds are actually going to lead to some bit of raw key. Okay, so in order to formalize what this state looks like, we need to modify the measurement process that Alice and Bob perform at the theoretical level. We need to formulate it as a multi-step process. For instance, we need Bob to first do a measurement that just tells him, am I going to get a detect event or a no detect outcome? And only then he learns his bit value of the actual item. Okay, we have this acceptance event here. Yes, so we have this acceptance event, and this event must be well defined for the states that we are writing down, right? Which means that, okay, all the testing information that we're going to use to accept or reject the protocol, all those measurements have to be performed and publicly announced. And this can pose a problem if you have information from key generation rounds that you're also using in order to decide your testing, right? So you might use Z basis for key generation, but if you're also using the measurement outcomes of those Z basis rounds to decide whether you accept or abort, then it's not clear whether you can write down a state like this, right? And this is a problem that shows up, for instance, in the one decoy protocol, and there are methods to solve it. And you can look at poster 219 by Jerome, who is here. But the point is that in order to use this technique, you have to first write down what this state is. And when you choose to write this state down, you'll realize that certain things are complicated. Okay, for instance, you can't put the error verification event in here, because in order to put that in here, you have to make Alice and Bob measure in the Z basis all their key generation rounds. And if they have measured in the Z basis already, then you can't talk of virtual measurements in the X basis when you apply the EUR state. Okay. Notice we don't need to squash. We don't really care about Bob's measurement per se here. As such, we are going to kind of use data processing to make Bob be classical, etc. And so we don't need to squash when we use it. Okay, how do we bound the phase error rate? Kind of basic example looks something like this. In each round, we first decide, do we get a detect or no detect measurement? We discard all the no detect measurements on Bob's side. Then we do basis choice. We discard all the basis mismatch rounds. Some rounds Alice and Bob measured in the X basis, so we observe some X basis error rate there. Some rounds they measured in the Z basis, and we want to bound the min entropy that goes up in here. And if we instead measure these rounds in the X basis instead, we have this phase error rate that we wish to bound, right? And this relationship follows from entropic uncertainty relations. And this connection ends up being some kind of a random sampling argument where you say that I'm basically doing the same measurement here and here. I'm just randomly assigning some rounds to test and some rounds to key. And so some classical random sampling statements can be used. Okay, so I cheated a little bit when I drew this diagram. In reality, Bob does basis choice first and then decides whether he's going to get a detection or not, right? So this kind of commuting of these two steps is not always true, and it requires sort of strong assumptions on the detection setup, which goes by the name of basis efficiency mismatch. Similarly, having the same measurement in the testing rounds as the phase measurement in your protocol also requires restricting your analysis to kind of perfect qubit BB84 sources, which is also a kind of strong assumption. And the point I'm trying to make is that the core proof technique here does require some high symmetry assumptions. Okay? This is not that much of a problem. These symmetry assumptions can be relaxed. On the source side, they have been relaxed in many, many works. On the detector side, they have been relaxed. These relaxations can be combined. So we have ways to bound the phase error rate and use them in security proofs for both source imperfections and detector imperfections without strong symmetry assumptions. But the analysis, at least for me, does look a little bit convoluted, right? You end up having to make figures like these to convince yourself that you're not going wrong. And I think I can say these are painful because I made this one. So as a whole, this proof technique is not as modular as one would like it to be. Like typically, in order to combine source and detectors, you need a kind of fresh proof that redoes a big chunk of the analysis. And it's not obviously applicable to completely generic protocols, although it does work pretty well for BB84-like scenarios. But many works have succeeded in obtaining these bounds for a variety of imperfections, which are very well studied. And actually, most of these bounds are analytic, right? So you don't need fancy numerics to run your period computations, and it yields pretty good periods. All right. The last proof technique that I want to talk about is entropy accumulation theorems, right? So there are a variety of entropy accumulation theorems. All of them kind of sort of look like this. You have some sequence of channels that at the end of it produces Eve's quantum side information, the raw key register, and all public announcements. You have some condition on these channels that must hold. If this condition holds, then you get a resulting bound on the entropy that you care about that looks something like this, where the first term is some single round quantity that you hope to be able to compute. And the second term is this log probability term that ends up becoming the probability prefactor in the security definition that we spoke about earlier. Okay? So the way you use this proof technique is you write QKD as a sequence of channels satisfying this condition, and you evaluate the single round quantity. Right? And typically the first step is not that hard, I think, but the hard part is actually being able to compute the single round quantity. Okay? So for today, I only want to focus on this new variant of the EAT called marginal constraint EAT, which I'm going to call MEAT. Amir is going to give a talk on this, I believe, on Friday. So please make sure you attend that. The way we're going to use it in QKD looks like the following. So these M channels in red are the ones that we're going to apply the entropy accumulation theorem on. Each of these channels first does Eve's attack, where Eve gets to hold on to some quantum side info from the previous attack, do some operation, forward a B system to Bob, and then keep some quantum side info for the rest of her attack. Then in each round, the QKD protocol does the measurements on Alice and Bob, makes public announcements, does sifting, and produces the raw key register. And actually, you can also give all public announcements to Eve at this stage. And so she can now choose to use that information in the way she attacks the next. So on-the-fly announcements are inherently included in this kind of channel structure. We start this thing off with Eve holding all of Alice's signals. So there are no sequential assumptions whatsoever, which was a big problem in the earlier generalized EAT approach. Eve does not touch the A systems at all, and so the promise or the marginal constraint on A is preserved, so it works for prepare and measure. And actually, these channels have some fairly minimal conditions on them. Okay, they can in fact be different for each round. You can honestly analyze some pretty wonky protocols where you say, I do 6-state protocol on odd rounds and BB84 on even rounds, and this EAT theorem would still work, right? Which I think is pretty cool. But it's a very, very new technique, and so there are not many papers out there that are kind of exploiting all these fun features. Note that this is a special case of, this is a general case of a EAT theorem that looks like this, where we don't have on-the-fly announcements, but where we basically don't have on-the-fly announcements. And this has been analyzed by other people as well and proved separately. And at the end of the day, in both of these scenarios, we end up wanting to compute a single-run optimization problem, which I don't want to write down because it looks a bit complicated. But the important thing to know is that it has this fixed marginal constraint inside of it. And so it works for prepared and measured. This is convex, and Lars has already figured out how to compute it. He will tell you more about it in this talk. Okay, so we can compute key dates using meat. Okay, so now in the last 2-3 minutes, we can talk about how the different proof techniques perform. This is the plot for qubit BB84. Okay, where we compare meat, EUR, and post-selection. Post-selection key rates are pretty low, no surprises there, and meat outperforms EUR slightly. And this figure is taken from, was made by Lars, and he'll tell you more about how to compute the meat key dates in his talk. Okay. When we go to decoy-state BB84, the plot looks a bit like this. So here the comparison is a little bit more nuanced. Ideally, we would want to optimize over all 3 parameters for all the proof techniques, but that's numerically costly. And because of the way decoy analysis works, these are slightly different protocols here, but I think the moral still stands. Post-selection key rates are still low, and meat still outperforms. Okay, so there are a variety of other criterion one might use to compare proof techniques. Things like, can you handle imperfections? Can you handle different protocol choices? What kind of computational resources do you need, etc. I realize this comparison is subjective and it changes as a function of time. And so we have this kind of comparison table in the paper, which you can take a look at. It will also be on poster 43, and I'm happy to talk about it with you. And with that, this is our group, and I want to thank you for your attention.
Thank you for the talk. Are there any questions? And maybe more importantly, where should they go to ask the question? Okay, maybe I'll start asking. So first of all, you mentioned that Eve has knowledge as to the number of photons, but doesn't really know what the intensity is. Is there any physical motivation for this?
Yes, in the sense that she picks an intensity, and then that leads to a photon number distribution. And the output state is block diagonal, so she can measure what photon number came out, but that does not tell us what intensity was used. Right? So, I mean, you can kind of do Bayes' rule and look at what is the probability of this pulse being from different intensities conditioned on me looking at a photon number of 3, and that distribution we can compute, but it's not a delta distribution.
And maybe one more question. So you mentioned that the post-selection technique does really bad, in part because you have assumptions on the measurement structure? Or is there a different reason for it?
So the performance is bad because of just that the GNX, like the dimension-dependent constant, is just too big. And so that just kills your key rate. The assumptions on measurement structure is more of, can we even use the post-selection technique? So if you have correlations in your in different rounds, then the measurements are not IID, and so you can't justify the permutation invariance of the protocol itself. And so you're technically the key rate that you get from post-selection is 0 because you can't make it work.
Okay, thank you very much. I'll ask maybe one more time if anyone has questions, and maybe because this room is very large, maybe stand up. Oh, there's one question over there.
I was just wondering, when you showed the graph comparing the techniques, there seems to be the post-selection technique missing here. So you don't have the curve for the, okay, now I see, sorry. So this means because it goes to 0 afterwards, because you only have 2 points in this graph.
Sorry, can you repeat?
I'm talking about the post-selection technique, the green triangles.
Yes.
Why you don't have all the points? Because the rate goes.
Yes, so yeah, they did go to 0 after that. And that has to do with kind of the way your numerics is set up. Like sometimes it just doesn't work beyond a certain loss. Yeah, and the numerics for like the meat plots are slightly different from the numerics for the post-selection plot. So that might be one of the reasons why the kind of the value up to which we are getting key rates for these proof techniques from numerics is slightly different.
There's another question over there.
Hi, Devashish, and thank you very much for the very instructive talk. My curiosity is about what happens. Imagine that I want to set up a decoy-state BB84 experiment tomorrow. What is my relationship with security proofs gonna be like? Do I have to start looking at them before deciding the specific of the protocol? Do I have to implement the protocol and then decide what is the most suitable security proof? Do I have to try applying all of them and see which one is yielding the better performance? If you can elaborate on that, I think it would be awesome.
So that's a good question. So I would say that you should definitely do it in parallel. You don't want to do it after you've implemented something. One example that I can give here is depending on proof techniques, we can either handle on-the-fly announcements or we can't, right? And sometimes we can handle on-the-fly announcements with imperfections in certain proof techniques. Sometimes we can either handle imperfections or on-the-fly, but not together. And so this kind of space is fairly complicated. And you might experimentally want to implement on-the-fly announcements because you don't want Alice and Bob to store all their measurements until the end of the whole protocol. And then if you know that, okay, there's a proof technique that the one that I'm going to use is capable of handling on-the-fly and imperfections, then I can simply design my system in a way that implements on-the-fly and not worry about it. If you kind of, yeah, I mean, I think overall, I think if you just implement a reasonable protocol, there should be some proof technique that works, but it might take time for people to figure out how to make it work for your implementation. And so I would say it's probably better to keep an eye out on what do we know we can handle currently with what proof technique, and then proceed.
Okay, thank you very much.
Any other questions?
So thanks for your talk. So I have a question is, yeah, you talk about the entropy uncertainty relation. You say the event you condition on must be clear, and you say that the one decoy-state protocol does not meet these criteria. And I want to know exactly why it does not meet, why it's not, why the event is not clear in this case in the decoy-state method.
Okay. Yeah, I did speed up a bit over there. So, okay, we have this state, okay, and because we want to apply entropic uncertainty relations, we don't want to measure the rounds that we want to use for key generation. So the Alice and Bob here are still quantum, but we know that these are exactly the rounds that we are going to use to generate the key. And all we have to do is make Alice measure in the Z basis, and we know what key she has. Okay?
Okay, yes.
And then we want to apply entropic alternative relations and say, okay, now I have the Z basis, but then if I instead measure in the X basis, I have the phase error rate, etc., etc. Okay? Okay, so this is why Alice and Bob are still kind of quantum and not completely classical in this state. The problem comes in only if the way you decide to accept the protocol, it depends on what measurement outcomes you get from these guys. Okay? If you have a protocol that does that, then you can't write down this state, because in order to say whether this event occurred or not, you have to know what the outcomes of these measurements on these guys were, but you have not actually performed them. Okay? And if you say, no, I will perform them, then this entirely becomes classical, and then your EUR statement no longer gives you anything useful. So it is something that doesn't show up typically in QKD, because most of the time there are, or in many protocols, the test rounds are completely separate from the key generation rounds, and so this is not kind of a problem that shows up in, let's say, most protocols, but it shows up in protocols where key generation data is used for acceptance testing. Okay. I don't know if that helps.
Yeah, so the problem is not with the classical announcement of the intensity, or
No.
okay,
No,
okay,
no.
I see. Okay,
No.
I see. Thank you.
Thank you very much for the talk. So maybe one last round of applause.
Thank you.